In the last video, we looked at more invertibility properties and said, okay, well, if we have an n by n invertible matrix and the kernel of that matrix is the zero vector, and we also have linearly independent rows and columns, and if we reduce our echelon form, we get in. But this section is titled determinant, so where does the determinant fit in? Okay, if we look at a 2 by 2 matrix, okay, so a generic 2 by 2 is A, B, C, D, right? And we want to look at this, but we also first want to kind of look at the case when the determinant is 0, okay? So if we say the determinant of this matrix is 0, that's the same as saying that AD minus BC is 0, okay? Well, that's interesting, but what can we say? Well, we kind of need to separate it into cases. Okay, one case we can look at is the case where A is equal to 0. If this is true, then okay, that's first, and that makes AD equal 0. So then that means that BC, that product, has to be 0. So then, what do we get in this case? Well, okay, we have the case, like subcases, right? There's a case where B is equal to 0 because we know we have something like this. And then in order to get B, C equal to 0, either B equals 0 or C equals 0. So then I'd have something like this, okay? But when I have something like this occurring, this is, if I look at the columns, right, we don't have linear independence, right? So then that means that it's not invertible. Okay, so this case where both A and B are 0 can't happen. And if I look at the case where C is 0, right, then I have something where I have zeros in the first column, and then I have BD, right? But then this also is not linearly independent. So then that also means that it's not invertible. Okay, so I can't have this. So when I look at the determinant, these conditions aren't enough to connect the idea of determinants with invertibility. Okay, so then if I do not have this hypothesis, the hypothesis would be that A is not 0. Okay, so then it could be the case that B is equal to a multiple of A. Okay, so then I'm looking still at A, B, C, D. Okay, and from this condition, that really means that, okay, so I have A, Ka, and then C, D. Okay, but then if I have the condition 0 is equal to AD minus BC, well, then I can factor an A out, and I'd be left with D minus Kc is equal to 0. So then, and I assume A is not 0, so then D minus Kc is equal to 0, and then that means that D is equal to Kc, so then I get A, C, Ka, Kc, right? And then this, again, is not linearly independent and therefore not invertible. Oops. Let's erase that. Okay, so then all these conditions, if I look at the determinant as 0, I cannot have these conditions if I want an inverse matrix. Okay, so here are some conditions that might allow for us to say we have an invertible matrix. Okay, if we have an n by n matrix, the following are equivalents. This is a common acronym in mathematics. We use TFA. So columns of A are linearly independent, rows of A are linearly independent, reduced echelon form of A is in, and then these are all conditions that give A is invertible. Okay, and also when the determinant was 0, all the subcases I looked at kind of told me that I didn't get invertible or invertible matrix. So I have to have the determinant of A is not 0. So that's where we connect the idea of invertible matrices with determinants. Okay, we can certainly check in for a 3x3 matrix, and so we let the matrix be UVW. Okay, and then this formula for the determinant was from a long time ago, way back when we were still in the first book for calculus, when we were in that chapter 12 or whatever on vectors. The determinant of A is given by U dot producted with V cross W. Okay, and then if the determinant of A is 0, right, then either, okay, if we look at this, right, if we look at this and say that that's equal to 0, then either V cross W is 0, okay, and then if the cross product is 0, that means that W and V are not linearly independent, right? Because they would, if their dot product is 0, that means they are actually parallel lines. So then that means that A is not invertible. And then if the cross product is not 0, so if V cross W is not 0, right, but we still need to get 0 somehow, then that means that U is in the span of V and W. Why? Because then the dot product, so the dot product would be 0. Okay, so if U is in the span, then that means that the columns are not linearly independent, and then therefore that gives us that A is not invertible. Okay, so it seems to work in a 3x3 case as well as a 2x2 case, that we have to have this determinant not equal to 0 property. Does it hold in higher dimensions? Well, yeah, it does. But we'll get some more practice with that. So we've officially connected the idea of having an inverse means that the determinant is not 0. So now in the next set of videos, we're going to look at some determinant methods.